So I have here an example of an AND probability, something that we would think we could maybe do using our multiplication formula. But we have a little bit of trouble. These events are not independent, right? If I deal the first card, that changes the probability for the second one because it reduced the number of cards that were in the deck. All right, so how can we do this? Well, we need another concept first, right? It's this idea of a conditional probability, right? A conditional probability of an event is the probability of an event occurring assuming that another event has already occurred, right? And you see the way we write this, or we'll look at some examples in a minute. The way I would read this is the probability of B given A, right? And you see I've kind of laid it out here. Again, the probability of event B occurs assuming that A has already occurred. That's what that little bar means. Okay, so let's take a look at this one. Probability of selecting a high school student. This is the list we've looked at this table before, right? This is somebody did a survey. They went 384 people and they asked them first, what's your age? Second, what's your highest level of academic achievement? Right? So I want to know what is the probability of selecting a high school student, assuming that they're under 21. Okay, so this is the A. This is the B. So this is the probability of A given B. And the way you can think about that, given that, assuming that they're under 21, you can think of that as a filter, right? That says ignore everything in the table except for that under 21 row. Now calculate your probability, right? So what do we get here? This we want high school students, right? So this is the number of high school students in my filtered list here. That's 120 divided by the total. That's 128. That's my probability. This is what 0.0938. Okay, so we actually have a formula. There's a formula that we can use to do this. It looks like this. Right, the probability of A given B is equal to the probability of A and B divided by the probability of B. The way I remember it is it's the second probability, the second event that gets dropped down into the numerator. Right, so to kind of test this out, this is the same question we just answered. Right, this is the probability of selecting a high school student assuming that they're under 21. We should get the same result, right? This probability is what it is, right? So we can't get two different values. So let's see, what does our formula say? Well, first, again, let's be clear. A is selecting a high school student. B is they're under 21. So the formula says this is the probability of, remember, it's A and B divided by the probability of B. Probability of A and B, that's a high school student and they're under 21. Well, that's these 120 people. So that's 120 out of 384 divided by the probability of B. That's the probability of being under 21. Well, there's 128 people under 21 divided by 384. And look at what happens. Right, these 384s cancel. This is 120 over 128, and that's the exact same ratio, same fraction that we got before, 0.938. Okay, so let me give you one here. Right, try this one. You see, all I did was I reversed it. Right, now I have someone under 21 given that they had a high school education. So see if you can take the formula out for a spin, see what this comes out to. Okay, so this is going to be my A, this is going to be my B, right? So the probability of A and B divided by the probability of B, that's my result. A and B, that actually is still the same, right? That is under 21 and has a high school education. So that's still 120 over 384. And then what's going on in the denominator? Now, you see this part is different, right? This is the probability of having a high school education. All right, that's 259 people divided by 384. Again, this 384 cancel. 120 over 259, that's 0.463. Very different, right? Different results. So the lesson here, right? The reason I picked these examples, these conditional probabilities are not commutative. Okay, the order, which one gets to be what you're looking for and which one gets to be the filter, the given part, it matters, right? That's going to impact your final result. Okay, now we're in a position to answer my dependent and event, right? The probability of being dealt an ace and then a queen. Okay, well, here's what I'm going to do, right? I'm going to actually go back to my conditional probability formula. My conditional probability formula says the probability of A given B is equal to the probability of A and B divided by the probability of B. Okay, what I want is the and, right? I want to know the probability of A and B. So all I'm going to do is I'm going to multiply both sides by the probability of B. Kick it over to the other side. The probability of A and B equals the probability of B times the probability of A given B. Okay? In other words, we're going to calculate the first probability just as it is. Right? Then we're going to calculate the second probability assuming that the first probability happened. The first event happened. Right? So let's see how we're going to do this. I'm going to let being dealt an ace be A, and I'm going to let being dealt a queen be B. All right, so what does this tell me then? This is the probability of being dealt a queen times the probability of being dealt an ace given we already got a queen. Okay, what's the probability of getting a queen? There's 4 of them out of 52 cards. Okay, now, what's the probability of drawing an ace given that we drew a queen on the first card? Okay, well, if we drew a queen, there's still 4 aces in the deck, right? So this is still going to be 4. And here's where it's going to change. There are now only 51 cards, right? Because that first card is gone. It reduced the number of cards in the deck. My calculator tells me this is 0.006. There you go. There's the result. Right, there's my probability. This is how we do an and probability when the events are not independent. All right, so let's try another one here, right? Notice all I did here was I flipped them, right? I changed the order. Now I have a queen and then an ace. Okay, does that change the answer? Well, intuitively, I kind of think it won't. But let's see. Let's go to the formula, right? Now the roles are reversed. A queen is A and an ace is B. So I'm going to do the probability of B times the probability of A given B still. All right. What's the probability of getting an ace on the first draw? There's 4 aces, 52 cards. Now, what's the probability of getting a queen given that I drew an ace? All right, well, there's still 4 queens. Right, there's still 4 queens. Now, there are only 51 cards. And that's the exact same ratio. Right? It's the same product, the same 2 fractions. This is still 0.006. We get the same result. Right, so when we're talking about an and probability, right, the order in which we do the multiplication to which card we get first versus second. Ultimately doesn't make a difference. Or we're going to get the same result either way. Okay, so that ends our discussion of probability. I say it ends. This is going to carry on, right? Probability is going to be really a driving concept throughout the rest of our discussion of statistics. Specifically, going into our next chapter here, we're going to be talking about something called a probability distribution.